Module 3, Investigation 3, using and interpreting function notation. Recall that the formula for determining the area of a circle is A equals pi r squared, where A is the area of the circle measured in square inches, and r is the radius of the circle measured in inches. Let g be the name of the function that takes radius length of the circle as an input and outputs the associated area of the circle. Explain in your own words what g of r represents. Essentially, we're just renaming our function with g for area. We could say that the area as a function of r equals pi r squared. We could name our function a. But instead we're just letting g be the name of the function that takes the radius length of the circle as an input and outputs the associated area. So essentially we're just changing the name of our function. G of r equals pi r squared. So what does g of r represent? Well, it represents the output given any particular radius input. In other words, g of r represents the set of output values for the function g. You might even say that it represents the area given a particular value of r. It's important that we think about input and output here. R is the input and g of r is our output. Next question says, use function notation to represent, not calculate, the area of a circle whose radius is 3.5 inches, 8.2 inches, and 26.92 inches. This one's pretty simple. For the area of a circle whose radius is 3.5 inches, we represent that with g of 3.5. If our radius is 8.2 inches, we can represent the area with g of 18.2. And if the radius is 26.92 inches, we can represent the area with this expression here, g of 26.92. Notice that we are picking particular values of the radius. This generic function pretty much works for any possible input. We can make a distinction here. G of r represents the set of output values for a function g, and that r is arbitrary. Here in part b we've picked 3 different values of r, and those represent 3 different numbers, 3 different areas. Whereas this function describes the relationship. No matter which value of r we pick, we can get the output value, the area. Part C says, interpret what g of 4.9 equals 75.43 means in the context of the problem. So our input is 4.9. Remember that that's a radius. So whenever we have a radius of 4.9 inches, our output, g of 4.9, our area is 75.43 inches squared. So when the radius is 4.9 inches, the area is 75.43 inches squared. You could also say that when the input is 4.9 inches, the output value is 75.43. What does it mean to solve g of r equals 141.026 for r? Don't explain how to solve for r. Instead, explain what the solution would represent. So this g of r, remember that represents the area of a circle with radius r, and if the area is 141.026 for this particular value of r, if we solve for r, that would tell us the radius we would need to have an area of 141.026 square inches for our circle. So if we find the value of r such that g of r equals 141.026, what we are finding is the value of the radius that would result in the circle's area being 141.026 square inches. Determine the value of r such that g of r equals 141.026. So what we're going to do now is figure out what that radius would be. So we simply think about what our function g of r is. Remember that g of r is the area of the circle. It's equal to pi r squared right here. So see. So g of r equals pi r squared, and we know that g of r is 141.026. So we know that our output value, g of r, is 141.026, and that's equal to pi r squared. Next, we need to solve this equation for r. So I'm going to give us a little bit of room. I moved what we've done so far to the right and started again here on the left. If we want to solve for r, notice r is being squared, then it's being multiplied by pi. We need to undo this operation. First, we can divide both of our sides by pi. So we have 141.026 divided by pi is equal to r squared. So to find the value of the radius, we just need to take the square root of both sides. Since we have the radius is squared, we can undo that square with the square root. And we can just think, well, if r squared equals this number, then r equals the square root of this number. So r is the square root of 141 over pi. And note that we don't need a plus or minus here because the radius can only be positive. And then if you use your calculator, that's about 6.70 inches. So that's the value of the radius that will give us an area of 141.026 square inches. Question 2. Suppose P equals H of T represents the population of the city of Blacksburg, Virginia, T years after 1990. Using function notation, represent the population of Blacksburg, K years after 1990. So take a second to think about this. The key is just understanding the problem. If we want to represent the population of Blacksburg K years after 1990, well, our function h represents the population of the city of Blacksburg T years after 1990. So if we want to find out what's the population in year K, we just plug K into the function. That's it. Part B, describe the meaning of h of k plus 3. So k plus 3 is our input. Recall that that's the number of years after 1990. So let's see, k plus 3 just means k plus 3 years after 1990. And remember that our function h represents the population of the city of Blacksburg. So h of k plus 3 represents the population of the city of Blacksburg K plus 3 years after 1990. Part C, using function notation, represent a population that is 765 more than the population of Blacksburg in the year 1996. There's a couple things going on in this sentence. First, 765 more than the population of Blacksburg in the year 1996 tells us that we just need to add 765 onto the population of Blacksburg in the year 1996. So how do we find that, or how do we represent the population of Blacksburg in the year 1996? Well, remember our function h, it tells us the population t years after 1990. So in 1996, that would be 6 years after 1990. So we need t equal to 6. So we can simply write h of 6. That will tell us the population of Blacksburg in the year 1996. But we want to represent a population that is 765 more than that population. Simply h of 6 plus 765. Part D, using function notation, represent the change in population of Blacksburg from m years after 1990 to m plus 7 years after 1990. So here we're interested in a change in population. Recall that a change is the final value minus the initial value. So remember, our delta h is what we use to represent change. So delta h equals h final minus h initial. So the final population, that's going to be m plus 7 years after 1990. We can represent that simply with h of m plus 7. And then m years after 1990, that's just h of m. So there's our final population minus our initial population. H of m plus 7 minus h of m. That represents the change in population of Blacksburg m years after 1990 to m plus 7 years after 1990. We can even put an equal sign here. Next, for part E, we need to represent the average rate of change in the population of Blacksburg from m years after 1990 to m plus 7 years after 1990, just like in the previous problem. But now we want the average rate of change. And remember that the average rate of change is the constant rate of change needed to, in this context, have the same change in population in the same amount of time. So to find the average rate of change, we simply calculate the ratio, a rate of the change in height over, not the change in height, I'm sorry, the change in population over the change in time. And that change in population, as we saw from the previous problem, is just h of m plus 7 minus h of m, divided by the change in time. Well, the final time was m plus 7 and the initial time was m. Notice that when we subtract those, the m's cancel out, we get 7, and that 7 just represents the change in time from year m to m plus 7. There was just 7 years in between. And this is our average rate of change. This expression represents the constant rate of change that would be required to have the same change in population in the same amount of time. And this needs to be a G. Oh well. The population may not be changing at a constant rate, but what this expression tells us is the constant rate of change that we would need to have the same change in population in the same amount of time. Part F, what is the meaning of 5 h of k? That's just 5 multiplied by h of k, and remember the input is just k years after 1990. So we're essentially taking the population k years after 1990 and multiplying it by 5. Number 3. The following table represents the price in dollars of a new Toyota Camry as a function of the number of years in after 2000. What is the input quantity and what is the output quantity? So recall our definition of function. When we say a new Toyota Camry as a function of the number of years in, then Toyota Camry is the dependent variable, the number of years in is the independent variable, the price of the Toyota Camry is the output, and the number of years in is the input. Part B says to evaluate each expression and describe the meaning in the context of the problem. F of 7. F of 7 represents the output of our function when the input is 7. Now we know that the input is the number of years since 2000, so our input is 7. And when we have that particular input, our output is 19,925. The price of the car in 2007 is 19,925. Now part 2 is 2 times f of 4. First of all, f of 4 represents the price of the car 4 years after 2000, or in 2004 we can look at our table and see the price of the car is $19,875. That 2 times f of 4 just means that it's twice the price of the car in 2004. Maybe we're buying 2 cars or something. So we could say the cost of 2 Toyota Camrys in 2004 is $39,750. Part 3, f of 7 plus 1,250. Well, f of 7 is just the price of the car 7 years after 2000. That's 19,925 plus $1,250. And that comes out to $21,175. So we can say that the cost of a new Camry in 2007 plus an additional $1,250 is $21,175. In a real-world situation, this could be the price of the car plus perhaps interest on a loan. In part 4, we have f of 6 minus f of 3. So the price of a Camry in 2006, which is $19,545, minus the cost of Camry in 2003, $19,045. So that comes out to $500, and we could say something like the cost of a Camry increased in $500 from 2003 to 2006. Number 4. Suppose the following graph of the function f represents John's weight in pounds as a function of time t measured in days since January 1st, 2008. Identify the input and output quantities for the function f. Notice that we have John's weight as a function of time t. So the time t is the input and John's weight is the output. Part B, evaluate f of 60. What does this value represent in the context of the problem? So simply take a look here. Here's when the input is 60. That's 60 days since January 1st. We can go up to our function and take a look at the corresponding y value, which is about, almost 180. We could say 179 or something. So f of 60 equals 179, and this means that John weighs 179 pounds 60 days after January 1st. Solve f of x equals 160 for x using the graph. Describe what each solution represents. So if we look at our graph, when f of x, the function output is 160. That means that John's weight in pounds is 160. We can see that that occurs here, and it also occurs right here and right here. There's 3 corresponding x values. That means there's 3 different days when John's weight was 160. We see that those are, let's see, about a little less than 20, maybe like 17. I'm right at 120, and let's see, a little less than 180, maybe 178. So again, x is 17, x is 120, x is 178. This means that John's weight, sorry, I keep misspelling weight or weighed for some reason. John weighed 160 pounds 17 days after January 21st. He also weighed 160 pounds 120 days after January 21st, and again 178 days after January 21st. We can see that his weight is changing as the days go by. Part D, what does f of 0 equals 140 represent in the context of this situation? So f of 0 is 140. That simply means that 0 days since January 1st, or on January 1st, John weighed 140 pounds. In Part E, we're asked to evaluate f of 200 minus f of 160, and think about what this difference represents in the context of the problem. First, we need to calculate f of 200. And looking at our graph here, when the input is 200, the output is maybe about 185. Then we need to calculate f of 160. When the input is 160, the output is just below 160, maybe about 155. So next we can calculate the difference. F of 200 minus f of 160 equals 185 minus 155, or 30. So what does this difference represent in the context of the problem? Well, we know that it's a difference in weight, and if we look at our graph, from day 160 to day 200, we can see that his weight increases. So we know that John's weight increased by 30 pounds from, let's see, 160 days after January 1st to 200 days after January 1st. So over the course of those 40 days, his weight increased by 30 pounds. Now, using function notation, construct an expression that represents the average rate of change of John's weight from 160 days past January 1st to 200 days past January 1st. What does this average rate of change mean in the context of the problem? Now, when we want to find average rates of change, we're just looking at the rate at which the function output value corresponds to the rate at which the function input value changes. Delta f over delta t, the change in the function value divided by the change in time. So from the previous problem, we found that f of 200 minus f of 160 was 30. The change in the weight was 30 pounds, and then the change in time, we can find just 200 minus 160 is 40 days. So 30 pounds over 40 days is 0.75 pounds a day. So how do we interpret what this means in the context of the problem? Well, notice that John's weight fluctuated over those 40 days. He didn't have a constant rate of change because there's not a linear function here. But if we want to consider the constant rate of change that would be needed such that he could gain the same amount of weight in the same amount of time, equivalent to the slope of the line connecting those 2 points, that's what we have here with the 0.75 pounds a day. So 0.75 pounds per day is the constant rate of change of weight with respect to time that would result in John gaining that same amount of weight, or 30 pounds, in the 40-day period. Number 5 says that functions are commonly used by computer programmers to access databases. All databases that involve time have reference times. One database uses a function named f to access the population of Pasco, Washington. This database uses a reference of 12 a.m. January 1st, 1990. So f of x represents the population of Pasco x years from 12 a.m. January 1st, 1990. So what does f of 2.3 represent? Well, that's simply the population of Pasco 2.3 years from 12 a.m. January 1st, 1990. What does f of negative 1.5 represent? Well, that would be the population of Pasco negative 1.5 years from 12 a.m. January 1st, 1990. So the negative here with the time just means it's 1.5 years before 12 a.m. January 1st, 1990. Part C, what does f of 238.75 represent? That's simply the population of Pasco 238.75 years after 12 a.m. January 1st, 1990. What does f of 4 minus f of 2 represent? This simply represents the change in population from 2 years since 1990 to 4 years since 1990. We could think about it as a final population value minus an initial population value, or the change. We could also think about this in terms of the actual number of years. 2 years after 1990 will be 1992, and 4 years after will be 1994. Okay, so parts E, F, and G, kind of interesting. What does f of 2 plus h, where h is some number of years, represent? Well, it's obviously h plus 2 years, the population h plus 2 years since 1990. But we might want to try to put this in a little bit more context. So also notice that we need to, let's see, like f of 2 would be 2 years after 1990, or 1992. And then we're adding h years onto that year. So we could say something like the population of Paco h years after 12 a.m. January 1st, 1992. So for part F, what does f of 2 plus h minus f of 2, where h is some number of years, represent? Well, that's simply going to be the change in population from 2 years after 1990 to 2 plus h years after 1990. We could also say that it's the change in population from January 1st, 1992 to sometimes h years later. Notice that we were dealing mostly with 1990, but when we introduce this idea of f of 2, that can be sort of a new reference point. So what does f of 2 plus h minus f of 2 over h, where h is some number of years, represent? Notice that this function would give us a change in population divided by a change in time. So this is a rate. It's a ratio. It's a rate of change. More specifically, it's the average rate of change of the population of Paco, Washington, from 2 years after January 1st, 1990 to 2 plus H years after January 1st, 1990. So, oops, put that in the wrong spot. Grab this. So f of 2 plus h minus f of 2 over h. I said that's the average rate of change of population with respect to time from 1992 to h years after 1992. It's simply a change in the function values, or a change in population over a change in the input values, a change in time, delta f over delta x. And remember, the average rate of change is the constant rate of change we would need to have the same increase in population, or same change in population, over that time interval h. So what does it mean to write f of 18.1 equals 55,246? That simply means that 18.1 years after January 1st, 1990, the population of Paco was 55,246. Number 6. Another database uses a function named G to access the population of Richland, Washington, which is 10 miles away from Pasco. The database uses 12 a.m. January 1st, 1995 as its reference time. So G of U represents Richland's population U years from 12 a.m. January 1st, 1995. Represent Richland's population on 1190. So notice that 1190, while that was the starting time or the reference time for our previous problem in number 5, now our reference time is January 1st, 1995. So that's like our zero position. So we actually are going 5 years in the past, so that'll be a -5 for our input, and we can express that as G of -5. So G of -5 represents his population 5 years before January 1st, 1995, which will be on January 1st, 1990. Represent the combined population of Richland and Pasco on the 1st of January, 1991. So for Pasco, that's from the previous question, that'll be f of 1, because we're 1 year after 1990. And for Richland in 1991, that's 4 years before our reference point, so that will be G of -4. Now, we want the combined population of Richland and Pasco on that date, so we simply take the population of Richland and add it to the population of Pasco. G of -4 plus f of 1. That's the combined population of Richland and Pasco on January 1st, 1991. Part C, represent the combined population of Richland and Pasco H years after the 1st of January, 1993. So with Pasco, H years after 1993, well, 1993 is already, let's see, 3 years after our reference point. So we can represent the population H years after 1993 as f of h plus 3 for Pasco. And for Richland, that's 2 years, 1993 is 2 years before our reference point of 1995. So we're basically going -2 years, and then we're adding on h years to that. That'll simply be G of -2 plus h. And since we want the combined total, we simply add these together. G of negative 2 plus h plus f of 3 plus h. Again, the G of negative 2 plus h is Richland's population 2 years before 1995 and then 8 years after that. And here we have Pasco, the population 3 years after 1990 plus 8 years after that. Number 7 says we could have said something like, let C of x represent the combined population of Richland and Pasco x years after 1/1/87. Part A says define C of x in terms of f and g. Okay, this problem you'll have to think about for a minute. So I went off and did some side work over here. If I want 1987 to be my new reference point, then that's going to alter my functions a bit, because I need, well, let's see what we need. Take a look at f. This is for Paco. If I plug 0 in for x, that will give me the value of Pasco's population in 1987, f of negative 3. And then if I skip up to x equals 3, that'll be 3 years after 1987. That will be 1990, and then I'll get back to normal. I'll have f of 0. Same thing here with g. 1987 is 8 years before 1995, the reference point for g. So we can combine these two functions to get c of x. Okay, so either one of these expressions will work. F of negative 3 plus x plus g of negative 8 plus x, that's equivalent to f of x minus 3 plus g of x minus 8. This is a tough problem. You might need to have some more time to think about this one. What does c of 17.25 represent? Well, that, just based on our definition here, represents the combined population of Richland and Pasco x years, or 17.25 years, after 1987. So it represents the combined population of Richland and Pasco 17.25 years after January 1st, 1987. Now if we add 17.25 years onto 1987, we get to 2004, and that 0.25 tells us we're a quarter of the way through the year. Now we need to represent the combined population of Richland and Pasco halfway through 2010 using the function c. So halfway through 2010 tells me we're going to need a 0.5 on our answer. And then we just need to subtract 2010 minus 1987. So you can check 2010 minus 1987 is 23. So we're 23 and a half years after 1997. That's c of 23.5. And that's how we represent the combined population of Richland and Pasco halfway through 2010 using the function c. And we could plug in that number to the function c and get a value if we wished. Number 8. Evaluate each of the following. Part A. f of 2x plus 3 when f of r equals r over 4 plus 2r squared minus 6r. So don't be afraid of this one. Just take a second and think about what it's asking us to do. We have a function f in terms of an input r, and you can see that the value of the output is determined by this rule, r over 4 plus 2r squared minus 6r. And we would just want to find the value of the output f when the input is 2x plus 3. So we simply replace r with 2x plus 3 everywhere here in the expression. So that'll give us something like this. F of 2x plus 3 equals 2x plus 3 over 4, just replacing that r with 2x plus 3, plus 2 times 2x plus 3 squared and then minus 6r. But instead of r, we're going to write 2x plus 3. We've substituted 2x plus 3 into our function. The next problem asks us to find g of 4 minus g of 2.1 when g of p is 2 square root of p plus 14 divided by 8 minus p plus 5. So all we got to do is substitute 4 into our function, make 4 the input, get the result, and subtract 2.1. Not 2.1, subtract what we get when we plug 2.1 into our function. So note here that I've just calculated g of 4. I've plugged in 4 in for p. 4 is my input. 2 square root of 4 plus 14 over 8 minus 4 plus 5. Now I need to subtract g of 2.1, which is just 2 square root of 2.1 plus 14 all over 8 minus 2.1 plus 5. Now it's really important here that I put parentheses around this whole expression, because notice if I don't, I'm just subtracting this first part of our expression, but I'm really subtracting g of 2.1, which is this whole piece. It's crucial that you put the negative or the parentheses there. If you don't, you'll get the answer wrong. Now just use your calculator and figure out what the value of this expression is. You should get something like 0.7612 approximately. Alright, let's try part C. h of 2 plus k of 3 when h of x is 4 raised to the x plus 2x minus 7 and k of y is 4 over 9 square root of y to the 4th minus 3y minus 5.1. All we're doing is taking 2 and substituting it in for our input x, and taking 3 and substituting it in for our input y, as follows. Alright, so notice that I've simply taken h of 2, which is h of x but with a 2 in place of the x. It's 4 squared plus 2 times 2 minus 7. And then k of y is k of 3. That's 4/9 square root of 3 to the 4th minus 3 times 3. I just replaced these y's with a 3. And subtract 5.1. And then that should come out. Just use your calculator. I think this comes out to 11.67. The book's answer is 14.5, but I can't get that. I don't know how they got that one. So check this yourself. Make sure you can get a good answer for this one. Number 9. Given the existence of some function t and b, I'm guessing that means there's two functions, use function notation to represent the change in the output value of function b over the input interval from -3 to 6. So remember that a change in the output value is just the final value minus the initial value. So here the input's changing from -3 to 6, so we simply need b of 6 minus b of -3. Part B. Use function notation to represent the sum of the function t at an input of -4 and the function b at an input of -1.3. So the sum, that means add. We want the function t with an input of -4, and we're finding the sum, so we're going to add the function b with an input of -1.3. Part C. Use function notation to represent the average rate of change of the function b from an input of 5 to 9. So we simply need the average rate of change of the function b as the input changes from 5 to 9. So we simply need the change in b over the change in time. We need b of 9. That's our final value of the output, minus b of 5, our initial value. Now I said time, but it's just really input here. We don't know if that's time. It could be number of cupcakes or something. So that's it. We can simplify this a little bit. B of 9 minus b of 5 over 4. And that's pretty cool. I just had an insight into calculus that h is always just the change in time. But more on that later.